Here we have the graph of the distance that a car travels after so many seconds. So seconds on the x-axis and distance traveled in meters on the y-axis. So let's take a look at 6 seconds. We can see that the y value is 9, so the car has traveled 9 meters after 6 seconds. But what we want to focus on in this lesson is how fast is the car traveling at 6 seconds, not how far has it gone. That's a pretty wild concept. You would think, well, we can't figure that out because we just have a distance graph. But the point of this lesson is you can figure it out. So let's take a look at this illustration right here. So let's draw 2 points. We know at 6 seconds it's gone 9 meters. At 8 seconds, let's drag this label over here, it's gone 16 meters. We can find the average rate of change of this line by dividing the change in y over change in x. So from 6 to 8 seconds, that's a difference of 2 seconds, so the change in x is 2, and the change in meters is 7. If we take 7 and divide by 2, we get an average speed of 3.5 seconds. So the question is, how does that help us understand how fast it's going at 6 seconds? Well, what we're going to need to do is take this green point, or its second data point, and drag it closer to 6. So what about at 7 seconds? Well, the change in meters is 3.5. It's gone 3.5 meters longer from 6 to 7. Change in seconds, it's 1. And therefore, its average speed would be 3.25 meters per second. So the concept is, if we can get a data point really close to 6 seconds, then we can get something really close to how fast it's going at 6 seconds. So I'm going to drag this green point closer and closer to the black point. Now we can see our change in meters is about half, and it's within 0.1 seconds. So the thing is, if we can get this point almost exactly to the black point, it will give us a pretty good approximation of how fast the car is going. And in fact, if we put the point right over top of 6 seconds, we can figure out exactly how fast it's going. In fact, we can show that it's going 3 meters per second at time t equals 6. So that's a great illustration, but how can we do this practically by ourselves? That's what we're going to learn in this lesson. So if you draw a point on a function, and by the way, this is a quadratic function. If you draw a point on a function, and this is at, looks like x equals 5, you can actually figure out how fast that function is changing. And just go back to the illustration we just looked at for cars. It's kind of like speed. We want to know the instantaneous rate of change at that point, not just the average rate of change. That's denoted by change in f over change in x, or change in y over change in x. So what would be the instantaneous rate of change of f over the change in x at that specific point? So what we typically do is we start out with, to conceptually understand this, we start out with 2 separate points. We start out with our initial point at 5, 4. We want to figure out how fast the function is changing there. We draw a separate point, and we're going to start, for example, at 2 units away x. So we're going to start at 7, 10. Now if we calculate the change in y6 over change in x2, we get 3. And if we want to think about our speed analogy, the function will be going 3, the average rate of change would be 3 meters per second from time t equals 5 to t equals 7. But what we want to do is take this point and make it closer to 5. So that's exactly what we're going to do. We're going to go to 6. So our new point on this quadratic function is 6, 6.5. Our change in y is now 1, and our change in x is 2.5. If we do change in y over change in x, we get 2.5. So the concept is that our new point is going to be more accurate representation of how fast this function is changing than our previous point. So we want to take this point and get even closer and closer to 5. So take 6 and take this point and drag it down closer and closer to 5. Let's try 5.1. What would be the average rate of change from 5 to 5.1? That'd be pretty close, right? The points would be almost on top of each other, so that's what we're going to do. So if we zoom in on our quadratic function at 5.1, we get a y value of 4.205. So our change in y is going to be 4.205 minus 4, so 0.205. Change in x is going to be 0.1, and if we divide change in f over change in x, we get 2.05. So it looks to me like the instantaneous rate of change is 2, right? This is a very, very close approximation to it. So the whole idea of instantaneous rate of change is you take these secant lines and you drag them closer and closer, and you make these 2 points closer and closer to each other until the secant line practically represents the instantaneous rate of change at 5. We can see that the limit of the slopes of these secant lines as the points get closer and closer to each other will in fact represent the instantaneous rate of change. So the limit as x approaches 5 of f of x minus f of 5 is equal to x minus 5. And again, that's as long as we ensure that this x value is getting closer and closer to 5. We call it infinitesimally close. So we would want it to be what? Like 5.00000001 and make it closer and closer. The tangent line touches the graph at exactly 1 point. So that's what I tell my students a tangent line is. Now let's take a look closely and see what that looks like. Alright, I've got my quadratic function here. I'm going to take my second point, drag it closer and closer to my first point. Let's need to plot it there. So we're going to take that point. Let's draw the secant line so you can see what it looks like. I'm going to drag it closer and closer to my, and I'm even going to zoom in to my initial point. And you can see that once it gets right over top of it, it's going to draw that tangent line. It's the orange line. Notice that line only touches the point, the graph once at the green point. It doesn't touch anywhere else. We'd have to zoom in really far to see that because I have the line thickness set so much. But the point is, it's just the tangent, the secant line eventually becoming right on top of that point to become the tangent line. So my definition of a tangent line is it touches the graph at exactly 1 point and it represents the instantaneous rate of change at that point. The tangent line is the limit of the slopes of the secant lines. Again, as the second x value becomes closer and closer and eventually becomes on top of the first point. The slope of the tangent line in this case then would be the limit as x approaches 5 of f of x minus f of 5 over x minus 5. The slope of the tangent line would be 2. Another way to explain it is the term instantaneous rate of change. It means the same thing. It means the slope of the tangent line. Now, we can use this notation to represent an instantaneous rate of change. As your second x value gets closer to your first x value, so in this particular case, as the 5.39 gets closer and closer to 5, what happens? The change in y over the change in x will represent the slope of that orange line. So what that means is the slope of this purple line gets closer and closer to the slope of the orange line until it becomes that slope when these 2 points become 1. That's exactly what this expression stands for. So the slope of this tangent line is the same as instantaneous rate of change. Its limit as x2 approaches x1 of f of x2 minus f of x1 over x2 minus x1. This is the same as, your slope that you learned in Algebra 1, y2 minus y1 over x2 minus x1. It's just that you're dragging 1 point closer to another one. Okay, so that's going to be it for this example. I would say take this app, play around with it a little bit. Notice your change in y over your change in x, and notice that the slope of that secant line gets closer and closer to the point of the slope of the tangent line as these points get closer to each other until it ends up right on top of it and those slopes are the same. Alright, that's going to be it for this video. If you have any other questions about it, let me know.